So we're going to round out this series of friction slides with a misconception question and one more friction question that basically applies to everyone's life. Okay. The misconception question, it's the one with the little book on the table. So if you guys can go there. It says a physics textbook lies on the floor. Okay. What is the magnitude of the frictional force on it from the floor? Okay. So it's just sitting there at first. We have this little book, right? This little textbook. Right. And I have a normal force going up and a weight going down. Right. Now, no horizontal forces applied to it. What would be the frictional force? 0, right? The frictional force only exists if it has to resist some motion, right? There's no motion that it needs to resist here. There's no one's pushing anything, right? But part B says, if a horizontal force of 5 newtons is now applied to the book, but the book does not move, what is the magnitude of the frictional force? So I put 5 newtons here, right? But the book does not start to accelerate. Well, if it's not accelerating, that means that the frictional force must be opposing it at exactly 5 newtons. And this is S for static. Okay? All right? So in that case, the frictional force would be 5 newtons. Okay? Now it says if the maximum value of Fs possible, right, the max this could possibly be is 10 newtons, will the block move if the magnitude of this guy is moved up to 8? Well, if this moves up to 8, the frictional force will also move up to 8. And is it allowed to go up to 8? Yeah, it can go up to 10, right? So it still won't move in that case. And the magnitude of the frictional force will still be 8 newtons. Okay. It says, will the block move if it is moved up to, if the horizontal force is moved up to 12 newtons? Okay. Well, here's what happens now. This guy over here is moving up to 12 newtons. This guy up here will get to 10, right? And he'll immediately stop. This frictional force cannot exceed this. So now it's going to begin to accelerate because you will have a net force, F net, of 2 newtons. And a net force now can actually cause an acceleration. Okay, and this book will begin to move. So at 12 newtons, yes, it's moving. Okay? Take a moment to think about that, ponder it while I erase so that we can go to the next slide, acceleration due to friction, with all the puppies in the back of the truck. Puppies make me so happy. I hope they make you happy too. Okay. So while this applies to puppies, it actually applies to anything that is in something that's accelerating, right? So it's a really interesting question where if you have like a truck, right, like this, yeah, like the most, detailed, perfect drawing of a truck that there ever was, right? And you have a puppy on it, right? The tail, right? Okay, so we all know that there's some acceleration that this truck goes at, right? In which you end up accelerating so fast that the puppy slips and falls off, right? Notice, he's not actually moving backwards. He's not accelerating off the back of the truck. What's happening is the truck is accelerating out from underneath him, and he just like falls straight down, right? Now, from the perspective of somebody in the truck, it looks like he's fallen back, but that's not actually what's happening, right? Okay, so in order to analyze this question of what is the maximum acceleration of this truck so that the dog actually does go along with the truck and doesn't slip off. I feel like we're hurting a lot of creatures in this week, and it doesn't feel good in my heart. Okay. Anyways, what is that maximum acceleration such that this poor guy does not slip off, right? All right. Well, like all problems, we want to answer this the same way, all right? We want to begin by exploring the free body diagram, okay? All the forces acting on Fido over here, okay? So what do we know? Well, we know that Fido has a weight, obviously, okay? That's an easy breezy way to start, always. And we know that if he has a weight, he's pushing down on this surface, and the surface has to push back on him, and that's always called a normal force, okay? Now, there's something else that has to be acting on Fido, okay? Because he is accelerating in that direction with the truck, Okay, what is that force that's actually accelerating Fido? It's not the force of the truck. The truck has its own engine, and that dog's not bolted into the truck, right? So that's not what's doing it. So what is actually accelerating the puppy? Well, the answer is a lot easier if you think of what if this bed was made of totally of ice, the slickest, smoothest, perfectest ice that you've ever come across, right? What would happen in that case? Well, obviously, the second this thing goes, the puppy's sliding, and he's going to slip right off, right? But if it's kind of a rough surface, the puppy will probably go along. So what does that imply about what's actually accelerating the puppy? All right? It implies that what's accelerating the puppy is actually static friction. Okay? So anytime it could be a human standing in the back of a truck. It could be, a human standing on a merry-go-round that's being accelerated, right? If you're not slipping, it's because frictional force is actually accelerating you. Okay. So the question then is, all right, what is the maximum acceleration such that you don't exceed this frictional force? Okay. And to kind of spell that out a little bit more, I'm going to look at the two Newton's laws equations going on for this guy, right? So for starters, I have summation of forces in x must equal max, like usual, right? And I have the sum of the forces in y must equal to may, like usual, okay? I'm going to start in y this time, just for funsies, okay? What's going in the positive y direction? N, my normal force, obviously. What's going in the negative y direction? The weight, as usual, right? And is the puppy floating into the heavens? No. Is the puppy falling into the bottom of the earth? No. This must be 0, right? Which means that the normal force, okay, experienced by this guy is equal to his weight, or just the mg of the puppy. Okay? Now, let's look at the x direction. In this case, we do have an acceleration because we want this puppy to go along with the truck, right? This puppy is going to accelerate at whatever acceleration is the truck, right? So that ax is really going to be the acceleration of the truck. So that's his acceleration. But what force is accelerating him? Well, there's only one force going on in the x direction, right? And that is this static frictional force. So I'm going to put an Fs right there. Okay? Now, Fs we know is mu n, right? And we know that n is weight, which is mg. So I'm just going to put mu mg. Okay? And now my m's cancel. Okay? And so the acceleration of the truck then is just whatever the static friction coefficient is times gravity. Okay? In other words, this truck cannot accelerate faster than, it says that the coefficient of static friction is 0.09. It cannot accelerate faster than 0.09 times gravity, which is 9.8 meters per second squared. Okay, which when I multiply these guys, I get 0.882 meters per second squared. Okay, so this is what this tells us. If this truck accelerates faster than this rate, right, if it increases its velocity faster than 0.882 meters per second every second, then this poor dog, Fido, will slip off the back and fall down while the truck moves ahead. But if you accelerate less than that, right, you just have this nice slow acceleration, the puppy friction will actually allow him to accelerate with the truck, and your best friend doesn't go anywhere. Okay? So this concludes the static and kinetic friction part of the lessons. In the next few videos, we're going to be talking about drag and resistive forces.